Welcome to the Explainer. Okay, let's dive straight into this. When most people picture ethical hacking, they're probably imagining endless lines of green code scrolling down a black screen in some dark room, right? But actually, here's a really surprising fact. The absolute most unbreakable security barriers out there, they aren't written in software at all. They are literally etched into physical silicone. Ethical hacking goes way, way beyond just software. It's deeply rooted in the tangible, physical components of the machine itself. So you might be wondering, why exactly does physical hardware dictate the rules, the boundaries, and the actual speed of an attack? Well, it's because an ethical hacker isn't just battling some abstract software logic floating around in a vacuum. To be successful, they have to actively navigate the strict, unyielding physical limitations of a machine. Think about it. If you don't fully understand the physical board you're playing on, you simply cannot win the game. Let's start our tour of the machine with Section 1, the foundation, looking at architecture layers. Basically, architecture layers are the foundational hardware levels that an ethical hacker interacts with directly. Like we said, hackers don't just attack abstract code in the ether. They've got to directly interact with and manipulate these underlying physical structures to actually find vulnerabilities. It's kind of like being a master safecracker. You can't just guess the combination, right? You have to physically understand and manipulate the individual metal tumblers clicking around inside that lock. Moving inward, we hit Section 2, the brain, where we'll look at CPU permission boundaries. Now, what's really interesting here is how the CPU acts a lot like a medieval fortress. On the outside, we have Ring 3, or user mode. This is your everyday environment where standard applications run safely. It's kind of like a bustling, happy playground right outside the castle walls. But inside, heavily guarded, is Ring 0, or kernel mode. And wow, this is the ultimate prize for an ethical hacker. It's the core command center with absolute unrestricted access to the actual hardware. These CPU execution rings absolutely determine your permission boundaries. And it's so crucial to understand that these aren't just, polite suggestions from the operating system. No way. They are absolute physical laws built directly into the silicon itself. If an exploit runs in Ring 3, it hits a literal hardware-level wall the second it tries to execute a Ring 0 task. Next up, we descend into Section 3, the volatile workshop, also known as RAM. Okay, so inside RAM, things get pretty chaotic. This is the volatile workshop where programs are being built and run in real time. So the crucial point here is taking a second to untangle these moving parts. First, you have memory allocation, which is basically handing out the physical workspace. Then you have registers like EAX or RAX, depending on your system's architecture, and these act as high-speed hands holding immediate data. Finally, data pointers. These are literal directional signs pointing to exactly where information lives. It's a live, breathing construction site. So why do we actually care about these specific elements? Well, because of exploits like the buffer overflow. This is an attack where understanding that volatile memory allocation, those exact registers and the data pointers, is absolutely vital. Picture pouring a massive gallon of water into a tiny little cup until it spills all over the control panel. A hacker deliberately manipulates those exact data pointers and overflows the allocated memory, forcing the machine's physical workspace to execute rogue code. This isn't just random software trivia. It is the exact physical mechanism required for the hack. Zooming out a bit, we arrive at Section 4, the speed limit, focusing on storage bottlenecks. Comparing modern and legacy storage brilliantly illustrates the whole race cars versus the horse and buggy situation. Modern SSD and NVMe drives read and write data almost instantaneously. Meanwhile, a legacy hard disk drive is literally a clunky, spinning metal platter just mechanically trying to keep up. The actual hardware you're attacking physically restricts your data flow. It can quite literally turn an exploit step that should take milliseconds into one that takes agonizing minutes. Those standard input and output bottlenecks completely control the pace of an attack. Think about it. No matter how incredibly fast the hacker's own computer is, or how brilliantly optimized their exploit code might be, they are completely at the mercy of the target's physical drive speeds. A lightning-fast script running against a painfully slow spinning drive is just going to sit there and wait. Let's see how this builds into real-world actions. In the field, this hardware reality dictates literally everything. Check high-speed asset enumeration or multi-threaded fuzzing sweeps. Both of these techniques require throwing massive amounts of data at a system to find weak points. A fast NVMe drive allows these sweeps to finish up while you go grab a cup of coffee. But an old HDD, that might drag them out for days. Your bottleneck is entirely physical, not digital. So we've navigated the foundational architecture layers, checked out those strict execution rings of the CPU, untangled the volatile workshop of RAM, and hit the absolute speed limits of storage drives. It's so easy to think our computers are purely digital magic, but every single piece of software runs on real silicon, metal, and wire. So I'll leave you with this. How are the physical components of your own machine currently exposed to these hardware level vulnerabilities?